Okay, so let's talk about addresses and the view that we see here in memory and the content and how this is all working out. So if you look at the addresses, so there's a couple of things we can actually discuss. So the first point is that you notice that this address is actually given in hex. Um, a lot of the data that we look at is provided in hex. This is a good way, a good trade-off. Like you don't want to see a lot of binary numbers. Hex usually is a good way to view the data and count and do the counting in assembly. And I'll explain why maybe in a minute. So if you take a look at this, you'll see that you have 1, 2, 3, 4, 5, 6, 7, 8, 7, 8 zeros here. So the reason that we have 8 bits or 8 hex digits is we have 32-bit address space. And 32-bit address space basically divided by 4 will give you 8. And why do we divide by 4? Well, we divide by 4 because counting in hex, we go from 0 to F. 0 is 0, 0, 0, 0, and F is 1, 1, 1, 1. So each of these digits essentially is 4 bits. So let me open up a notepad and go over this in a little bit more details. So let's start with binary. So let's say we have 8 bits of binary, 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits in binary will equal to 1 byte. So this is going to be equal to 1 byte. Now, as we said, 4 of these will be a word, and that will be 32 bits. 4 times 8 is 32. And if we count in binary, we go from 0, 0, 0, 0 to 0, 0, 0, 1, 0, 0, 1, 0, and so on. But if we want to count in hex, a hex value typically goes from, let's go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we need to keep it under one in one digit. So what comes after 9 is A, then B, not like B, C, D, E, and F. So if I would like to represent these values in binary, how many bits do I need? Well, the smallest value is 0 and the largest value is F. And to represent 15 in binary, I need 4 bits that are equal to 1, 1, 1, 1. And 0 in binary is 0, 0, 0, 0. 1 is 0, 0, 0, 1, and you guessed it, 0, 0, 1, 0, 0, 0, 1, 1, and so on. 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and now you repeat the same thing, and actually, so 1, 0, 0, 0, 8 is 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and then finally 1, 1, 1, 1. So basically, again, hex value is occupying or requires 4 bits to be counted for. So if I have now remove this from here, actually I can put it on the bottom. So now I have 32 bits of addresses, right? 2, 3, 4. Remove the spaces here. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So basically now I have an address space that is 32 bits. My address space in this architecture in assembly is 32 bits. And here I have them. So 1, 2, 3, 3, 4. Oops, I actually copied way too many. So 1, 2, 3, 4. So these are 32 bits. And to represent these in in hex, you can easily split them like that. And now I can transform or translate those bits into their hex equivalent using 4 digits at a time. So what I'm trying to say here is that I'm not going to evaluate, well, let's do this example first. So the first 4 bits are equal to 0, second 4 bits also 0, third 2 bits also 0, 0, 0, 0, 0, and 0. So now this value in binary split into what they call these 4 digits nibbles actually. So it's like a half a byte. It's just 4 digits. So now this is my hex representation of that value using 4 digits at a time. Okay, so let's say I have the following address. So I'm gonna copy this and this. I'm gonna use them here. So let's say I have this address, just hypothetical example, right? So how does this translate? What does this translate to? So the first digit is 0. So from 000 binary, it is 0 hex. 1100 is C. That's 12, and 12 is C. And then 0, 0. This is 8, 0, and then this is 4 and 0. So now, if you look at these numbers, you will see that basically you have 0x, 0, 4, 0, 8, 0, 0, C0. So now this is a value that is representing 32 bits, okay? And that is essentially what I'm looking at when I look in the memory addresses in the program, the coding, the Altera Monitor program. Basically, when I'm looking here, I'm looking at those addresses. So the first address is 00000000. Basically, this is telling me this is the very first address locate, or this is the very first location in memory that is starting at 32, actually 32 bits of 0. That's the first location. And then the next one is 00000001. However, you notice that we're going from 0 to 4. Like it feels like we're almost stepping up, or we're counting up by 4. And let me explain why this is happening. So this is the second part of this video. It's like why we're going in 4s. And for that, let me open another sheet here. Okay. So if you take a look at this numbering, this is going actually in hex, and I'm counting from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. After that, it becomes 1, 0, and again here it will be 1, 1, 1, and then 1, 2, and then 1, 3. And you guys see where this is going, okay? And then 1, 4, etc. But when we look at the memory in our assembly code memory addresses, we see that it goes from 0 to 4, 8, C, 0, 4, 8, C, and so on. So I'm going to highlight these fields. So this is essentially saying that each location actually holds let me backtrack just for a second. When we did the byte declaration, we saw that 1 byte, for instance, let's say we have a byte that is residing at this location. We saw, let's say the byte was equal to 41, which is the hex value of A. And then after that, there was the subsequent declarations that we had in memory. So whatever comes here, some values I'm just going to randomly write, these are all bytes, right? And so on. So this byte, the very first one, 41, actually is occupying 1 space. And then the other ones are occupying 1.5, 1.6, and 1.7 respectively. So this is something that you need to keep in mind. So if I'm declaring a byte, this byte will reside in one memory location. So each memory location is holding one byte of information. So if I declare, if I have a dot, for instance here, dot byte 55, okay? So in this memory location, I will see the value of 55 and whatever that is in hex. So let's see, 55 decimal will be 37 hex. So you will see 37 here, 0x, right? You will see 37. Okay, and so on. So in our example, when we had dot byte a, b, and c like that, what's going to happen is the value of a in ASCII, the hex value of a is 41, b is 42, and c is 43. So these three values are going to live or sit in the addresses 1, 2, 3 respectively. After that, we had another ASCII declaration that was also ABC, but we used the ASCII directive. So again, we had 41, 42, and 40. Sorry, it was lowercase. So 61, 62, and 63. Again, 61, 62, and 63. Now, when we look at the memory in the assembler or the monitor program, what happens is that the GUI, the interface, is going to hide these from you. It's going to lump sum those into one location like that, and it's going to concatenate those back to back. So this is going to be 61, 62, and 63 like that. Okay, and the same thing goes here, 61, 62, 63. Like that. You don't see it like this, and then basically this is moved up like this, and then actually these two are also moved up like that. And then here you have the dot ASCII ABC. Okay. So on the top of that, so this is what you see in, on the top of that, you can actually even declare, change the view of this. So this is what we were looking at, what we were looking at, 61, 62, 63, 61, 62, 63, and they live in the address space, just as I explained in a minute. On the top of that, what you can do actually is you can view multiple words per line. So you can actually view 2 words per line, or you can view 8 or 4. So if you do 4, you notice that the counting is now going up. This is the first word, which is the first 4 addresses, and these 4 addresses are holding the 4 bytes, followed by the next 4, followed by the next 4, followed by the next 4, total of 12. So this first address is actually starting at address 0 plus C. C is 12, and 12 is the beginning of the 4th byte, or the 4th the 4th word, right? So the first one goes from 0, and it goes to 0, 1, 2, 3. Then this starts at 4, goes 4, 5, 6, 7. The third one goes from 8, 8, 9, A, B. And then the last one starts at C, C, D, E, F. And then what comes after F? 1. So like 0F is the last address in that 4-word display, and the next one will be 1F. And that's how this is going. It feels like it's jumping from one location to another, but it's not. All of them are there. What I wanted to mention here and I wanted to focus on is each location holds 1 byte. That is one rule that we have. Each location is holding 1 byte. Each 4 bytes constitute 1 word. And the addresses typically are grouped into, at the very least, into words. So number of words, where is that? So if I do this, so at the very minimum, I am looking at 4 bytes at a time. okay, or the addresses in this GUI is going up by 4 locations at a time. You can think of it that way as well. Now, you may ask why we're concatenating 4 bytes at a time. This is a 32-bit architecture, so if you have 4 bytes, you have essentially each byte is 8 bits, so you can essentially grab 4 8 bits or 32 bits um, from that location plus the the 3 locations that are subsequent to that. So basically, you're grabbing 32 bits of data at a time per se. It's a 32-bit architecture. We have 32 bits to represent the addresses that we have. And when we do display or put data on the bus, we're grabbing 32 bits. And how many bytes are in 32 bits? There is 4 bytes. And that's why this view is most common and it makes more sense to us. Now, the last point I'm going to mention here is, let me go back to that declaration that we have. So at some point we saw that some of these words are actually starting sort of like on an odd address. This is not the beginning of a multiple of 4. So this was the this value right here. This is that one because A is 41 followed by this 1, which is a word, and we say that this is occupying 1, 2, 3, and a 4th byte on the next line. So is there a way to fix this? Can we make this 1 actually starts on a clean, quote unquote, new line? And the answer is yes. We can use an align directive for that. But for that, we can, we'll table this for the next lecture. In this one, I hope that you learned how viewing the memory address in the GUI is done and why is it 32 bits and how we can translate those bits into hex values and how we can read the address in hex. Thank you for watching.